Last week, we have discussed cross-validation. In the cross-validation chapter, we have discussed how to estimate the test error. So where we basically split our entire data set into two different parts or several different parts. And then from the disjoint subset of your entire data set, you can test your trained algorithm to understand what is the test error for a new observation. So in most of the case, the test error is the most important thing, and we want to minimize the test error. And in machine learning process, usually we have several options. For instance, in the regression task, we can select a subset selection, which means among p different input predictors, we can choose one or two input predictor so that we can optimize the test error. So why we have to choose the subset? So let's consider this case. Let's say n is the number of data point and p is greater than or equal to n. Let's consider this case. In this case, if you use the full input predictors, then the linear regression task use this model. So y is equal to beta 0 plus beta 1 x1 plus up to beta p xp plus epsilon, of course. And the RSS value will be defined like this. Beta 0 minus beta 1 xi1 minus beta p xip square. So why the full input predictors can have some problem or can have some issues? So usually when p is greater than n, we can fit every data point without any error, without any mistake. We can perfectly fit the yi using the p plus 1 number of parameters, using the beta 0, beta 1 of the beta p. Since we only need to fit n different data point and n is less than p, so we can make some perfect result. So we can make RSS is equal to 0. Okay, this is very nice for training process, but the problem is in terms of test error, usually when you fit every data point perfectly, it is kind of memorization, and this is overfitting. And this can cause a huge test error. So when you look at a new input data point, usually when your algorithm is overfitted, the outcome will be very far from the true value. Your estimation for any new input can be very bad because your parameters are very overfitted. So to reduce the overfitting or to resolve the overfitting, we have to find a subset of your input predictors. But in this process, we cannot randomly select a few input predictors because among p number of input predictors, of course, there is some important input predictors and there are some redundant. So we have to very carefully choose subset of input predictors. This is one thing. And also we don't know which size is the best. We don't know how many input predictors are key to predict the output, right? So we have to learn some kind of model selection algorithm. So here the model means, what is the model? Model is the subset of your input predictors to estimate the output y to define the linear regression model, right? So this is the one simple example why we have to implement some model selection. And for classification task, we have to decide either implement LDA or QDA. If your data points are very simple and very easy to discriminate with linear boundary, then we have to implement LDA. But if your boundary is more rounding or more complicated, it might be better to use QDA, because if you run the LDA and get the linear boundary, usually the linear boundary can introduce a huge bias error, and so we might lose many things. Okay, so for the model selection, so this is one model and this is model, and model selection means we have to choose LDA or QDA. So in the model selection process, we can, of course, we can use cross-validation. Cross-validation is the most powerful algorithm, for model selection, and we can use the cross-validation for any type of model selection process. Okay, so we can use cross-validation for the subset selection for linear regression case. We can use cross-validation for choosing QDA or LDA, or you can use the cross-validation to choose the support vector machine or some other very complicated model, what we will discuss in the later of this class. So we can use the cross-validation in many places, in many situations. So remember, cross-validation is the very powerful approach to select a very nice model. But in many cases, not many cases, but in some special cases, we have very nice model selection technique which can overcome some bottleneck of cross-validation, some weakness of cross-validation. So what is the weakness of cross-validation? So usually cross-validation do not utilize the full data. When you have this amount of data, we usually split your entire data into training and test. Well, k-fold cross-validation, of course, we use more data for training and very small part, 1 over k portion of your data point for test. So, but still, you waste some of your data. You do not use some of your data for training, and for estimating your test error, you just use very small portion of data. So there might some error, right? There might some randomness to estimate the test error. So maybe cross-validation might be long. Okay, maybe the cross-validation give you some very bad algorithm or model instead of very nice model. Maybe, with some chance. So when you're model selection, considering very simple model like a linear regression with input predictor selection, subset selection, we can consider some other type of model selection approach. Okay, so what was the weakness of the cross-validation? In the cross-validation, although we have this amount of data, we just use very we just use some part of our data, and we waste this amount of information for training, right? So the other approach, what we will study this week, is we will study some model selection approach that can fully utilize the entire data. Okay, like AIC, BIC, or Ritchie regression, and lasso.